another episode of Learning sCrypt tutorials. In this video, I'm going to show you how Bitcoin signatures work. So we all know when we spend some Bitcoins, a typical way is to sign with our private key to show we are the legit owner of the Bitcoins. So how does the signature algorithm work? So here we have a simple diagram. So this is a general description of how digital signatures work. That also can apply to Bitcoin. So initially we have some message. We want to sign it from the sender, and once receiver receive it, he can verify the signature is a proof that it is actually sent from the sender and the message has not been tampered with. So how does this work in detail? So first, we have like in Bitcoin, we have a private key and which has a corresponding public key. So the signature algorithm, there are two parts. The first one is how do we generate the signature. Basically, you have the message, you can apply the private key, and then together you can get an output. Usually we call it the digital signature. Once we have the digital signature, along with the message, we can send it to the receiver, and the receiver, they can use the signature, the message, plus the public key to verify if the signature is valid. If it is yes, that means in Bitcoin context, we can move the coins. If not, the coins cannot be moved. Okay, so we just talked about how signatures in Bitcoin context work. So just as a side note, in reality, in practice, for most digital signatures, instead of signing the whole message, which can be long, for performance reasons, we usually hash it. So the same thing happens in Bitcoin, which we hash the message with a SHA-256 hash algorithm. So then the next natural question would be, what is the message exactly here? What message is being signed here? So it's actually called a Sighash preimage because it's a hash, so it's called a preimage. And because this is the hash, is going to generate the signature, so it's called a Sighash preimage. So I think it consists of 10 fields. I think I'm not going to cover each one. It's a lot. So fail to say, it's mostly consists of the transaction that the signature is embedded within. So which is usually called the current transaction. So for example, you can see almost a one-to-one mapping from the preimage and the transaction format. So for example, you have a version number, you have version, you have let's say a hash previous output. You basically the corresponding to transaction ID here is the output that we're spending from. And also you have an end sequence, you have end log time, also you have end log time in the transaction. So by the way, on the right, we're showing the format of a Bitcoin transaction. And the only exception is field 5 and 2. So this is not part of the Bitcoin transaction, is in fact is a UTXO, the transactions input is spending from. So you can think about this as the script in the output of the UTXO, and this is how many satoshis are in that UTXO. So let's look at a simple example. With again, we are using the boilerplate, and we are using the pay to public key hash, which is the contract you are running when you send a normal Bitcoin transaction from Alice to Bob. That's basically is mostly checking the signature. We can see that's a built-in function called txSignature here. Again, as we mentioned before, you can use a debugger to run it. So here we already have the before we can configure the debugger as we did before with only one exception here, which is that's an additional field. Except all the other parameters, that's additional field called transaction context we have to provide for us to run any contract that involves signature checking. The reason for this is for signature, you have to provide the preimage so it knows which messages it is signed. And this transaction context basically give you all the information you needed to generate the preimage that the signature is derived from. You can also, again, we can go to the sCrypt.io homepage. If you scroll down to the desktop IDE, it has you can click the user menu. So basically, you can go to debugger, and in the config section, you have config section. You have this transaction context field, which is what we showed earlier. Basically, this transaction context field has a multiple fields itself. Basically, for example, it has hex. Basically, this is the serialized transaction. It can be signed or unsigned. And input index is which input in the current transaction we are talking about. And also the UTXO, how many satoshis are in it for us to spend. So here, let us go back and we can see we have all this field here. So as before, we can launch the debugger and run the contract. So for example, now we can click. Oops, let me bring out the debug console. Okay, now it says runs successful. We can try to run it again. Let me actually delete this so we can make sure this is up to date. We just run and it means successful. So we just showed how do you run any contract that involves signature checking. So how do we, when we launch this, we have to provide the signature, right? So how do we usually get these arguments here? So we can go to the unit test for this contract, which we showed in the last video. How do you run a unit test locally for any contract? This is just based on the contract, the testing file for this pay to public hash contract, and we can see the signature that's a helper function called sign transaction. That can, if you plug in, you can see this is a transaction context, and also you have the UTXO information, basically how many satoshis and what is the locking script there. Plus, you can provide the private key, which give you the whole signature. So once you have the signature, actually we don't print out here, but if you want, you can print out all the parameters here. So which then you can plug in into the launch.json. So we just showed you the success, how when it succeeded is good, but a lot of times when you are computing the signature, you can make mistakes. For example, let's slightly change one example here to see what happens. Let's say from 3, we just change it to 1, and let's rewrite. So we expect it to fail, right? Okay, it does fail, and let's keep running. So we notice that besides the usual error messages we get when we run any other type of contract, it also, in addition to those, it also gives us a hint, because txSignature is, you can think of, is more complex than typical primitive functions. So it's usually hard to see why the signature checking fails. So the debugger print out some additional hints for you to check why it fails. So for example, you may be using the wrong private key, right? That's definitely one reason. if you can remember, if you go back to how the signature is generated, basically it takes two inputs. One is the message, which is the Sighash preimage in our case, and then another input is a private key. So it only has these two possibilities. One is private key is wrong. It does not correspond to the right public key, or the Sighash preimage is wrong. So this is the standard preimage we expect. So basically you can see all the fields as we see in the format, right? So you can check each of this to see which field is not correct. So how do we do that? Again, we can go back to the documentation. We can go to exceptions. So basically that's a specific exception. Basically the signature check failed. It gives you more information for you to help you to pinpoint what exactly goes wrong. So in this example, because we can either check now private key is right, what about preimage, right? So you can also add an additional line here. You can go to the test file or whatever deploy file you have. You can actually compute the preimage that's used for the signature using this helper function, get preimage. And once you have this preimage, you can print out to the console. And then, as we showed earlier, you can compare it field by field, side by side with the error message print out here. So this hopefully can help you identify which field is not right. Okay. Okay, here is end of the video. I hope you enjoyed, and I will see you next time. Thank you.